Hi, thanks for watching. So today we're going to present some work on how person systems achieve near optimal compression. So this is work we have done with Noga, who will be presenting with me today, and with Jennifer Culverstone from the University of Edinburgh. So let's start by talking about person systems. Person systems are ways in which languages categorize or refer to individuals as a function of the role in the context of a speech. And the most typical way in which languages lexicalize person categories is by using personal pronouns. So for example, in English, we can use the pronominal form I to refer to the speaker in the context, and the pronominal form you to refer to the addressee. And we can also refer to other people who play no role in the context of a speech by using a pronominal form such as they, he, she, it, etc. Now, personal pronouns can also serve to refer to groups of individuals. So for example, in many languages, we have pronouns to refer to the speaker plus others with exclusion of the addressee. And this is what we do in English with the pronominal form we. So or at least we can express this meaning with the pronominal form we. And we can also express this meaning with the pronominal form mato in another language like Maori, which is a language spoken in New Zealand. Now, in English, we would use the very same pronominal form, we, if we want to express or to refer to groups that include only the speaker and the addressee. This is not the case across the board. So in a language like Maori, we would actually use a different pronominal form, like the form taua. So what we see here is that the reference to these person roles, the speaker, the addressee, and others, actually interacts with number, given a whole range of possible reference that pronouns can take. And this is what we are showing here on the left. And as we have seen by looking at languages like English and languages like Maori, languages are going to partition this space in different ways by mapping it into linguistic forms. So some languages are going to express all reference using unique forms. So for example, this is the case for Maori. So where we have 11 different pronouns, which are going to cover each of the possible reference in our space. Whereas some other languages, like English, are going to feature some homophony, such that some of the reference are going to be expressed by the same form. Now, there is a lot of variability in person systems across languages. And here we have a typological sample of 10 well-documented systems, which are actually the ones that we are going to use as data set for our analysis. And what we can see here is that there is quite a bit of variation. So we have different patterns of homophony that emerge, as we can see, like in most of these languages, except for Maori. And we also have languages like Mandarin, where there are multiple forms to express the same meaning. And that's what we are trying to convey by using this divided cell over here. Now, a natural question that arises when we are looking at this distribution is what are the computational principles that categorize the typology of person systems across languages? That is how we can explain the variability. So these questions have been addressed mostly by linguistic theories of person, and most of these linguistic theories have explained the typological distribution of person systems by proposing strong grammatical constraints. So the general idea here is that there is a set of features or a feature structure that fully determines how humans represent the person space. And it does so in such a way that only those person systems that are compatible with that structure are predicted to be systematically attested in the world's languages. Now, different theories are going to actually vary on what specific set of features they propose, but one challenge they all face is to strike a balance between overgeneration, which is failing to capture typological tendencies, and undergeneration, which is ruling out as impossible systems that are actually attested. Now, just to give you an example of this struggle, we can look at how linguistic theories account for a well-known typological observation, which was made by Zwicky in 1977. So Zwicky observed, and we observed in our first examples, that many languages can actually express this you and us inclusive meaning as a form of the first person. And this is what happens in English, where as soon as the speaker is part of the group that we want to refer to, we can use the pronominal form we, without paying attention to whether the addressee is part of the group or not. Now, Zwicky observed that there is no language that expresses this inclusive meaning as a form of the second or the third person. Just to put it differently, there is no language that uses the same pronominal form to refer to all groups that contain the addressee without carrying out the speaker. And there is also no language that uses the same pronominal form for groups that contain both speaker and addressee, or neither speaker and addressee. Okay. So this observation made by Zwicky is actually quite puzzling. And the reason why it's puzzling is because it seems to suggest that the speaker and the addressee might not have the same weight in our feature representation. So most linguistic theories that have tried to account for this observation have encoded an asymmetry in the representation of feature and addressee in the human mind. So, for example, it has been proposed that there is no addressee feature, and that's why we cannot have systems that are addressee-based, whereas there is a speaker feature, and that's why we can have speaker-based systems. Now, in recent experimental work, it has been revealed that actually learners are sensitive to both of these features to the same extent, to both addressee and speaker. And this seems to suggest that we do need a representation for both of these features. Now, so that's partly the motivation or this struggle between this struggle to capture typological tendencies is part of the motivation that we have to propose an alternative approach, which is based on an information-theoretical framework for semantic systems under evolution. So under this approach, the idea is that person systems are shaped by a soft bias towards communicative efficiency, given an underlying feature structure. And it does so in such a way that efficient systems are more likely than those that are not efficient. And the particular novelty of our approach is that we are going to leverage this framework for testing hypotheses about feature weights. So we are going to relate to previous theories, but we are going to do it in a different way. And now I pass to Noga.
Okay, thanks, Maura. So here's the main idea. Our approach is based on the hypothesis that languages efficiently compress meanings into forms by optimizing the information bottleneck between the complexity and accuracy of the lexicon. This principle gives us a theoretical bound on the efficiency of any person system, whether it is attested or not. This bound depends on their underlying representation of the domain. Therefore, if this hypothesis is true, then we expect that attested systems will tend to lie near the theoretical bound, given an asymmetry in the representation of the speaker and addressee, and this is exactly what we'll show. We're interested in this specific framework because it is grounded in rate distortion theory, the branch of information theory that characterizes optimal data compression. It has been supported empirically in several semantic domains, such as colors and containers, and it is closely related to the idea of efficient communication in semantic typology, which is not based on rate distortion theory, but has gained a lot of empirical support across semantic domains, including numeral systems and indefinite pronouns, which are qualitatively more similar to person systems. Therefore, the person domain poses an important test case for the applicability of rate distortion theory to the lexicon. So let's define this framework more precisely and apply it to the person domain. So this framework is based on a simple communication model in which a speaker mentally represents a target referent by a distribution M over some feature space that we will define later on, and then communicates this representation to the listener by encoding it into a linguistic form, W. The listener then tries to infer the speaker's representation by constructing an estimator M hat. According to the information bottleneck principle, the speaker and listener should jointly optimize a trade-off between maximizing accuracy and minimizing complexity, where complexity is measured by the mutual information between M and W, which is roughly the number of bits that are needed for communication, and accuracy is measured by the similarity between the speaker's and listener's mental representations, such that maximizing accuracy amounts to minimizing the KL divergence between M and M hat. If the speaker and listener are not willing to tolerate any errors, then the speaker will have to assign a unique form to each meaning, resulting in a complex communication system. On the other hand, if they're only trying to minimize complexity, this will give a non-informative system. Therefore, optimal systems should minimize complexity while maximizing accuracy for some trade-off beta between these two competing objectives. In order to solve this optimization problem and compute the actual theoretical bounds for person systems, we need to specify two components: a prior distribution over possible reference, which is often called communicative need, and the underlying representation of the domain, which defines the speaker's mental representations. So let's start with communicative need. In general, estimating this component is a major challenge because it is unclear how to measure directly the frequencies with which each referent to the domain is communicated. To address this, we use the recent inference method that for any given system finds the maximum entropy prior over the domain that is consistent with its corpus frequencies. We applied this method to 3 languages, English, Spanish, and Mandarin, for which we have both word frequencies from both the UD3 band corpus, which is based on written language, and from the childless corpus, which is based on child-directed speech. So here you see all the inferred priors, where the need probabilities for each referent in the domain are shown in grayscale. And as you can see, these priors are actually not extremely different from each other, suggesting that at least some patterns of communicative need may be shared across languages. So for simplicity, we take here the average prior distribution and treat it as a universal communicative need. And importantly, we will test this prior not only on the 3 languages from which it was inferred, but on all the languages in our data. The second component we need to define is the underlying representation of the domain. So following prior work, we defined the speaker's mental representations by a similarity-based distribution. However, this requires a similarity measure or distance function over the domain. So to define this function, we map each referent into a binary feature vector where the features correspond to the person in number dimensions. And then we take a weighted Hamming distance over the feature vectors. So now the question is, how should we define these feature weights? One simple way is by assuming that all features are equally salient, and we refer to this as the unbiased model. However, as Maura explained in the first part of the talk, there is evidence for an asymmetry in the representation of the speaker and addressee, suggesting that person systems may be shaped by a soft egocentric bias, favoring a salient speaker representation. In addition, a secondary asymmetry favoring participants in the conversation has also been proposed in the literature. So to formally test these proposals, we define an egocentric model in which these biases are reflected in the relative feature weights. So now, for each model, we can compute the theoretical limit of efficiency by solving this optimization problem given their underlying representation of the domain. So if the egocentric bias shapes person systems, in addition to pressure for efficiency as predicted by the theory, then the egocentric model should provide a better account of our data and should distinguish between attested and unattested systems. So here is the theoretical bound for person systems that was derived from the egocentric model. And as you can see, almost all attested systems are near optimally efficient according to this model, which means that they achieve near optimal compression. To see this quantitatively and to compare the 2 models, we measured the deviation from optimality of each system such that lower values correspond to higher efficiency. And recall that each model predicts that efficient systems are more likely to be attested. As you can see, almost all attested systems are more efficient under the egocentric model, suggesting that they are better suited for communication in the presence of an egocentric bias. In addition, comparing these results to the 2 unattested systems, according to Zwicky's observation, shows that the egocentric model predicts a substantial efficiency gap between the attested and unattested systems, whereas the unbiased model better accounts for the unattested systems and does not really separate them from the actual systems in our data. To test the significance of these results, we compared the attested systems to a set of hypothetical variants that were obtained by permutations of the data, and we found that under both models, the attested systems lie at the highly efficient tail of the distribution, implying that all languages in our data are non-trivially efficient. And finally, we tested the generalization of these results beyond the 10 languages in our data by considering a much larger typological data set, even though this data set documents only a reduced domain with 8 references instead of 11. We found that also in this data set, the vast majority of person systems are near optimally efficient given the egocentric model, and that the egocentric model outperforms the unbiased model. So to conclude, we've shown that person systems across languages achieve near optimal compression in the presence of an egocentric bias, and our analysis has also suggested that at least some patterns of communicative need may be shared across languages. More generally, our approach provides a principal way to study how cognitive biases may shape the lexicon and may explain typological tendencies such as Zwicky's observation without assuming strong grammatical constraints. However, an important direction for future work is to further test our models on a larger typological data set that documents the full person domain. So thanks for listening.